Okay, let us see an example. We have a function given here. Is it defined on the whole of real line? For x less than 4, some definition is there. For x greater than equal 4, it is there. It looks like it is defined over R, but let us see the definition. So, f of x equal to 1 divided by x minus 3 if x is less than 4. So, it says that at x equal to the function is not defined, right. So, when you find the domain of this function, you have to exclude these 3. Now, for x greater than equal to 4, it is 2x plus 3. So, it is well defined. So, that means this function is defined on R minus the point 3 to R. This is the domain of the function R minus 3, that is excluding the point 3. It is minus infinity to 3 union 3 to infinity, excluding that 3. So, suppose this is our function. Now, you want to see whether it is continuous at all these points or not. So, let us say we take a point C which is less than 3. It belongs to this interval minus infinity to 3. So, that means the first line, first condition of this function definition will be applicable. So, when you find C less than 3, 3 is a right end point here in the interval minus infinity to 3. Okay. But there is also a right neighborhood there, because the other condition says 3 to infinity. So, both the sides a deleted neighborhood, if you take deleted neighborhood of 3, that is contained inside this domain. So, it is not only one sided, it is both sided limits are there. So, the notion limit x goes to C is meaningful here, right, if C is less than 3. Even at C equal to 3, both the sides are meaningful. Okay. So, once we take C less than 3, the first one is applicable, it is an interior point, right, minus infinity to 3. So, C is an interior point here. Then we take limit f x, x goes to C. But first one is applicable. So, limit of x goes to C 1 divided by x minus 3, that limit, and it is meaningful, x is not equal to 3, it is less than 3. So, function is well defined, and as we know from the algebra of limits, its value will be 1 divided by C minus 3. But at C, f of C is also equal to 1 by C minus 3, that is equal to f of C. Therefore, it is continuous at C. So, you see the limit notion helps instead of going back to epsilon delta. Now, suppose C is a point between 3 and 4. Okay. C is between 3 and 4. So, because the definition of the function involves x less than 4. So, we are considering that case first. Again, the first one is applicable. So, f of x equal to 1 divided by x minus 3. So, what happens for limit? You see that limit of f x 1 divided by x minus 3, again the same way it will go, will be equal to f of C. Therefore, it is continuous there. Now, what happens at 3, if C is equal to 3 or C is equal to 4? C equal to 3, f of 3 is not well defined, it is not defined at all. Okay. So, the question of its continuity at 3 is meaningless, we do not consider it. So, we go to the another possible breakpoint is 4, where two different definitions of the functions are there. To the left of it, it is like 1 by x minus 3, to the right of it, it is 2x plus 3. So, we consider that as a special point 4 now. So, suppose we take x equal to 4. At this point, we cannot go to limit directly, because on the left it is defined one way, on the right it is defined the other way. So, let us take on the left definition, that is the left side limit we are interested in, x goes to 4 minus. So, limit of f x goes to 4 minus will be limit of x goes to 4 minus 1 divided by x minus 3. So, again from the limit computation as we did earlier, this x will be replaced by 4 from the algebra of limits, that should give 1 divided by 4 minus 3, which is 1. So, that is 1. So, its left sided limit at 4 is 1. What about the right sided limit? limit of f(x) x goes to 4 plus. So, the other one 2x plus 3 is applicable. We take limit 4 plus 2x plus 3, that is again from the algebra of limits 2 times 4 which is 8 plus 3 which is 11. So, that means limit x goes to 4 does not exist at x equal to 4. So, since limit does not exist, it is not continuous at x equal to 4. Okay. What about at any point which is bigger than 4? So, again this is the function f(x) equal to 2x plus 4, and we find its limit at any point c. C is an interior point in that interval. So, both side limits exist. Algebra of limits says that it will be equal to 2 into that c plus 4, which is also equal to f of c, right. Therefore, it is continuous at x equal to c. So, in summary, what we see here, that f(x) is continuous at every point of its domain except at x equal to 4, where the limit of the function does not exist. Is that clear? I think this is an exhaustive example which gives all kinds of things possible here. Okay, let us go to second example. Here there are various questions here, not one, but in all these functions we are given with many functions, 1, 2, 3, 4, 5, 6 functions are given. For all these functions, we want to find out whether the functions are continuous at x equal to 0 for each of them. So, how do we proceed? At x equal to 0 here, so y equal to f of x, it is a straight line given as a straight line. There is some point here, it is not exactly, it looks like smaller than 1, some function, right. This distance, had it been 1, it would have been y equal to x, but it is not, but it should go here. So, plus something is there, y equal to x plus this distance, but it is something else, its slope is not exactly equal to 1. Okay. So, but this function we want to find out at x equal to 0 whether this is continuous or not. As it looks, you do not have to lift the pen, you can draw including that point 0, at the point 0 f of 0 equal to 1. So, it should be continuous, that is what it says, right. Left side limit equal to right side limit equal to the functional value f of 0. That is what we say, that it is continuous at x equal to 0. Now, you go to the second function f of 0, it is a hollow circle. So, f of 0 is not defined, it is the same function as earlier in A, but at 0 it is not defined. So, once at 0 it is not defined, it is not continuous, that is clear, because we need the functional value, function should be defined at that point. However, here the limit of f of x as x goes to 0 exists and it is equal to 1, both left side and right side limit they are 1, but it is not defined at that point. So, it cannot be continuous. Okay. That is what we write here. Types of continuity, we will see at b the function is not defined at x equal to 0. So, it is discontinuous at x equal to 0. Now, let us look at c. So, in c what happens? It is the same function again as in A, except at the point 0 it is now defined, but its value is 2. So, what happens here? Left side limit of the function as x goes to 0 is 1, the value is lying near to 1, and the right side limit is also 1. So, limit of f x x goes to 0 is equal to 1, but it is not equal to the functional value which is given as 2. So, it is not continuous at 0. Now, what about the fourth one in D? Here when x is less than 0, the function is given as 0 itself, right, its value is 0, and when x is bigger than or equal to 0, its value is given as 1, that is the function. At 0 also its value is 1. So, now you see the left sided limit exists, that is equal to 0, right side limit exists, that is equal to 1. Functional value at 0 is 1. So, right side limit is equal to the function value, but left side limit is not equal to the function value. And we see that the limit of f x as x goes to 0 does not exist, because left side and right side limits are different. Therefore, the function is discontinuous at x equal to 0. So, in first case it is continuous, second case it is not continuous because function value is not given, third case it is not continuous because function value is different from the limiting value, fourth one is not continuous because the limit does not exist. Now, let us come to the fifth one. So, in fifth one, at x equal to 0, if you take the left side limit, it does not exist, it blows up to infinity, right. Left side limit is equal to infinity. The right side limit as x equal to 0 is also equal to infinity. So, the limit x goes to 0 equal to infinity here. You say that limit f of x, x goes to 0 is infinity. We do not say the limit exists. Limit exists means it should be a real number, but it is not. Infinity minus infinity are special cases of non-existence of limit. Though we can write in symbols limit f x equal to infinity, limit f x equal to minus infinity. All remaining cases we cannot even write that. But limit does not exist, it is infinity. And f of 0 is also not defined here, right. It is function is 1 divided by x square. Therefore, the function is discontinuous at x equal to 0. Of course, you cannot redefine it. You cannot say that f of x equal to 5, so that the function would become continuous, because limit equal to infinity. And we cannot say that f of 0 equal to infinity, that will not define a function, because infinity is not a real number. So, we cannot do anything, right. We cannot redefine at 0 to make it continuous, because limit is equal to infinity. Function becomes unbounded in a neighborhood of 0. That is what the fourth case is. Fifth case is. Now, come back to the picture, is the sixth one, let us say f. So, the function is y equal to sin 2 pi by x. So, here is the graph. In the neighborhood of 0, you see that there is oscillation of the function. It takes values from -1 to 1, okay. All these values it is taking near 0 when it is there. So, as we see, and the function value is not defined at x equal to 0. So, it is discontinuous. But can we redefine it in such a way that it will become continuous? We cannot, because it is oscillating, though it is bounded, unlike the last case. In last case, it was becoming unbounded in a neighborhood of 0. Here it remains bounded between -1 to 1, however, limit does not exist, and also function value is not specified. Therefore, it is discontinuous there. You can see various possibilities of discontinuity here. So, what we write is, we have all the others are not continuous at x equal to 0, though the types of discontinuity are different. So, in B it is not defined, in C limit is not equal to f0, in D right hand limit, left and right hand limits at x equal to 0 are different. So, limit does not exist, and E has limit infinity as x goes to 0, also function is not defined. So, we cannot redefine it also to make it continuous. In F, left hand limit nor the right hand limit at x equal to 0 exist. They do not exist because they oscillate. So, they are also f is not continuous. Is that fine? Now, let us continue to solve some problems basing on these notions. We have a function given as f of x equal to 1 minus square root of 1 minus x square. This is defined in the interval -1 to 0, -1 closed, 0 open, okay. And also the same way when it is in the interval 0 to 1, open interval 0 to 1. At 0 only we are not taking that 1 minus square root of 1 minus x square. that is f of x equal to 0 for 1 to 2. Okay. So, we have now 3 kind of things, minus 1 to 0, then we have 0 to 1, and then from 1 to 2. So, all that we have left is f0. So, f0 is defined separately as 1. That is how it is defined. So, in the interval minus 1 to 1, except at 0, it is 1 minus square root of 1 minus x square. In the interval 1 to 2, it is the constant 0, and f0 is 1. That is how it looks. So, we are asked to find the points where f(x) is discontinuous, and if possible we redefine at those points to make it continuous, if possible. Okay, so, it looks that the possible points are minus 1, 0, 1, 2, right. So, let us see how it goes. Now, f(x) is defined on minus 1 to 2 closed interval. Okay. It starts from minus 1 goes to 2. So, where it is continuous? It is 0 between 1 to 2. So, it is continuous there, right. At 1 we do not know, at everywhere else it is continuous there. Then it is defined from minus 1 to 0 and 0. So, at 0 possibility of discontinuity is there, otherwise it is continuous. So, the only possibility are 0 and 1. At the end points, of course, we can see that this function is continuous, because one side limit exists. On the other hand, the other side is also existing. So, only 0, 1 there are possibility, but we have to discuss whether they are or they are not exactly. It is just a guesswork now. So, now we find at 0, let us say. So, when limit x goes to 0 minus, we have the function defined as this 1 minus square root of 1 minus x square. So, we find its limit at x goes to 0 minus. So, algebra of limit says that it should be square root of 1 minus 1, it is 0, right. Now, when x goes to 0 plus, again the same thing we take, we see that x becomes again algebra of limits of 1, the whole square root is 1. So, 1 minus 1 again 0. So, the limit exists and it is equal to 0. What about f0? f0 is given to be 1, but the limit is equal to 0, right. So, that is why it is discontinuous at x equal to 0. So, in this case we can redefine our function. We will define another function g, which is just like f everywhere else except at 0. At 0 we give the value g of 0 equal to this limiting value, which is 0. Then that would make the new function g to be continuous at 0. Okay. So, that is the meaning of redefining f. Now, we will discuss at 1. So, at 1 again we go similarly, x goes to 1 minus f of x, again the same is applicable there. So, 1 minus square root of 1 minus x square equal to 1. Okay. Now, when limit x goes to 1 plus, that is from the right hand side, so this one is applicable. So, it is constant 0. So, the limit should be equal to 0. That is, the left side limit at 1 is not equal to the right side limit at x equal to 1, though both of them exist. So, that means limit of f(x) as x goes to 1 does not exist. So, whatever way we define f of 1, forgetting this f, but a new definition at 1 some other way, we cannot make it continuous, because this limit itself does not exist. That is what we say, the limit of f(x) at x equal to 1 does not exist. So, we cannot redefine it to make f of x continuous at x equal to 1. Okay. So, let us see another problem, at which points f(x) equal to tan of pi x by 2 is discontinuous. That should be quicker, because we know the behavior of tan. It looks like this, it is pi x by 2 instead of tan x. So, there will be a scaling in the independent variable, pi by 2 is multiplied with x here. So, this is how tan looks, right. So, what we see, when t goes to 2n plus 1 pi by 2, tan of t equal to plus or minus infinity, that is what we know. So, at those points it is discontinuous for the tan function. So, that is pi x by 2 equal to 2n plus 1 into pi by 2, right. Pi x by 2 equal to 2n plus 1 into pi by 2. Whenever this is satisfied, at those points x, we have discontinuity, right. Here discontinuity, here discontinuity. One side it blows up to infinity, another side it blows up to minus infinity. So, we say that at these points x which satisfy this, the function is discontinuous. So, that is x is equal to 2n plus 1, right. These are the only discontinuity points, everywhere else it will be continuous. So, that means whenever x equal to 2n plus 1, an odd integer, f x is discontinuous. At all the other points, this function tan of pi x by 2 is continuous. Okay. So, stop here.